This is aimed very much. Thanks everyone. So this talk was put together in a terrific hurry, so apologies in advance. And it's aimed very much at the younger or the newer researchers. The older people, like the people, old fogies like me, can have a nice snooze for 15 minutes or so. Hopefully you know everything here, and if you don't, it's too late anyway. Okay. So I'm gonna talk a bit about a few things generally relating to kind of how to use computers in doing scientific research. And it's a bit meandering and things, but it's generally things I've noticed that some new students or new postgrad students just don't do. So as I said, if everybody feels it's an incredibly boring talk, then that's a good thing. Okay. That means everybody's doing all the stuff already. So I thought to start off, let's take a problem that probably everybody can wrap their head around. Suppose that some politician's driven over a speed bump fast and has damaged his car, and now he's putting together a ministerial committee and dumped loads of funding into universities on how much damage speed bumps are doing to cars and how much the extra maintenance costs are. Okay. So we need to figure out the effect of speed bumps on road vehicle maintenance. Okay. There are lots and lots of ways we could approach this. So off the top of my head, I came up with three. So the one is we could actually go and gather data from Midas and all other places that do car repair, particularly working on suspension and the chassis and whatever, try and relate that to the number of speed bumps in the locale of each, like say within a few 5 kilometers of each one of these repair garages. Okay. And if you wanted to, you could gain additional data about the speed bumps, their shape and whatever, if it's available, their height. Okay. Alternatively, we could take approach which I'm quite happy with, or quite familiar with. We could try and develop an engineering model to predict based on physics, predict what's going to happen when the speed bump goes over the car. No, the car goes over the speed bump, other way around. Speed bumps, I hope the speed bump doesn't go over the car. Okay. The car goes over the speed bump, we can basically make a model of some sort, numerical model, hopefully verify and validate it against some experimental data, and then we can try and figure out what the likely damages are that you're going to have. Okay. There's another slightly like left of center approach we could take, and my ex-wife, who's an economist and also a lecturer at the university in the information sciences department, she recently did a project which kind of made me think about this. You could always look at something like what's it called? It's not Twitter anymore, it's now X. You look at the number of tweets that people have put up there complaining irately about the damage that the speed bumps have done to their car. And you could try and use that as a proxy. So hopefully you can see that any one of these approaches is going to have some issues, and then none of them are going to necessarily give you the full picture. So ideally, you want to do a bit of all of them. And also, hopefully, you're going to need to do a fair amount of computing in order to make this all happen. Okay. Like 150 odd years ago, you would have got a bunch of army of grad students and kept them in the room on bread and water until they did all the calculations for you, but that's not allowed anymore. And computers will generally make less mistakes than the starving students anyway. So now one of the problems is that trying to find these different approaches, trying to look at different approaches, we're introducing unconscious and conscious biases, assumptions. We're human, we tend to think about things in a certain way and discount certain possibilities. This can be a very bad thing. We can neglect obvious lines of, or not so obvious lines of research that we need to actually pursue if we want to get a true understanding of the problem. But it can also be a good thing because like if you take the naive approach, which some people today would advocate perhaps, and I'm not obviously people who don't know about such things, but I mean, if you tried to dump like 3/4 of the internet onto something and then ask some sort of super chat GPT like thing to give you data on speed bumps, you're going to get a lot of rubbish out, and a lot of the information you're feeding in has no bearing on speed bumps or cars. Okay. So, I mean, that's a highly exaggerated way of putting the whole thing, but the point is, because we have some understanding of problems, we're not just trying to blindly draw correlations as a machine would do it. We're actually capable of filtering out some of the more obvious blind alleys, and that's a good and a bad thing. It's a good thing if we get it right. It's a bad thing if we get it wrong. Okay. Now, I was very lucky when I was an undergrad student. The lead aerodynamicist for the Thrust SSC, which was the first car to break the sound barrier, the first land vehicle managed to break the sound barrier over a certain distance. He came to Stellenbosch, and I was in third or fourth year, and he came and talked to us about it. And he said that they basically did the whole design on paper first, using basic principles. And it was only after they'd done that that they checked their design and checked their assumptions using computational fluid dynamics. And this was an eye-opener for me at the time as a little third-year student, because I always thought you climbed onto the computer as quickly as possible. And evidently I wasn't alone. So the important thing to remember here, and it's something which is becoming increasingly difficult to remember, but therefore even more important to remember, is that computers, even something that looks like it, can fake it really well, like ChatGPT, they lack insight, they lack understanding, they lack a moral compass, and they lack originality. ChatGPT is very good at mushing up everything that is on the internet in 20-something or other, or 2020 or 2021 or whatever, and regurgitating it, something based on that to you, but it's not actually producing anything really original. I mean, we can argue about this. Maybe some of the guys who are more clued up on neural nets will disagree with me, but it's basically all based on a input data set, which you're doing funky things with. So you really don't want to use this to engage in intellectual laziness. There are two movies that generally sort of take vastly different views of the robot apocalypse. The one is two series of movies. One is obviously the Terminator movies, where the robots become intelligent and evil and want to take over the world. The other one is the kids' movie WALL-E, which I watched about 3,000 times when my younger son was born and my only slightly older son needed to be entertained. Quite honestly, WALL-E was actually a more likely and more plausible version of the robot apocalypse. We become so lazy and dependent on machines that we stopped actually thinking for ourselves. The idea of T-1000s wandering around mowing people down is rather far-fetched by comparison. So computers, robots, it's been always talk about this in terms of robots, physical robots with robot arms and tracks and things. They're for dirty, dull, and dangerous jobs. We really should be using machine learning, AI, and things for those same tasks. Things which are to some extent a bit mechanical or mechanistic. I don't want to say deterministic, because you can use them to solve stochastic problems and things. I know that. Not my, well, I suppose turbulence a little bit, but it's not my thing. But so you absolutely want to save yourself as much work as you reasonably can, but you don't want to try and excuse yourself from thinking. I can't stress this too. It sounds ridiculously obvious, but I actually had a very intelligent colleague suggest I needed to write a letter to excuse myself from doing something social that I didn't want to do. And I had a very intelligent colleague, and it actually wasn't a bad idea, but she told me to ask ChatGPT for an answer on how to do that, how to word it. And I went along with it. It did actually give me some ideas, but yeah, I mean, there's certain things which you don't actually want to be using a machine for. All right. Let's talk a bit about the kinds of problems you solve. Now, we talked about what you shouldn't be doing, a little bit what you should, and a lot more what you shouldn't really be doing when you're trying to solve a problem, like our speed bump problem, okay? I understand it like this. I kind of see there are probably other things, and people are welcome to tell me about them in the chat later. I appreciate it, but you can either, if you're doing fundamental science or something where there's a strong degree of interconnectivity in systems and a lot of variables which are horribly interconnected, like life sciences, economics, and so on, or with fundamental science that's not yet well understood, you're trying to understand the relationships between variables usually. You're trying to build a model of the system. There isn't a model. You're trying to build a model, okay? And this is where a lot of that stuff that Ila has been presenting the past 2 days comes in. Regression analysis, machine learning, those things really shine there, okay? Doesn't mean that some of the older techniques and methods are not valuable, but I mean, that's really where those things eat it up, right? You still got to use your head, okay? The alternative is, if it's a problem that is well established, you can do what engineers and applied scientists do, chemists, whatever, engineers, material scientists, I don't know, probably lots of other things, economists to some extent as well, when they are using simulation models, which they do. If you take a numerical model, which you to some extent understand, maybe you've tweaked it, maybe you've redesigned it from ground up, but it represents something where you have a fundamental understanding of the working of the system, and then you use it to try and predict the behavior of a given system or optimize it by tweaking certain parameters, various different ways of going about that, okay? there you're typically running some kind of numerical simulation. Okay? And the third one, which everybody has to do, and which Benjamin spent most of last week giving you tools to use for it, and me a little bit, and that is basically you've got loads of data from either one or two, or as a part of one or two, problems one or two, and you are trying to actually reduce it into a form where it's more easily manageable, either because you want to feed it into a simulation, or you want to feed it into regression analysis, or because you got all this data out of it, or sometimes processing the data is the problem. I mean, it's not exactly true, it's not my field, but I think in genomics and some of those things where you have to do sequencing of data, basically actually doing it efficiently is the problem. Okay. Right. So running out of time, so let's move on a bit quickly. So if you're trying to find the relationships, that's what they're using regression analysis, machine learning, those sort of things. Not my specialty. Ilya's been talking a lot about it much more competently than I can. So I'll leave it to the experts, but just a couple of comments which might be useful. I think they're sufficiently generally applicable. In the early stages, when you're actually investigating your data, you often have to take a very hands-on approach. You have to feel the way through it. And that's actually when you want to be using tools like Jupyter Notebook, or even Excel, or something like that, where you can actually intervene, you can fiddle, you can try different options quickly. Once you have achieved some level of understanding of what you're actually trying to do and what you need to do, you can then go and you must try and automate your task as much as you possibly can. You want to have no intervention if possible. You have to make sure you write ideally, you want to either get survey data or do an experiment and download the experimental data or whatever, and you want to run one script, and it must actually generate, at the very least, the figures and numerical tables for you, but ideally it could even generate a report for you. And yes, I know some people would say Jupyter Notebook does that. Yeah, if that works for you, good. I don't like the way it does it, but okay, that's also personal preference. Certainly, I wouldn't want somebody to put Jupyter Notebook as is into a thesis or an academic article, for instance. So that's why I'm saying it's not necessarily. To do that, you basically got to use a lot of the basic flow control tools in programming that we often try to avoid. If you're not that hot on programming, you want to use if statements to check for different conditions intelligently. When I say intelligently, I'm using it with a small I, not a big I. If that makes any sense. So that we basically just using making simple binary decisions based on things where possible, so that the human being does not have to intervene in the data processing. Okay. And also just remember, Ilya said this in a lot more detail yesterday, but you actually got to properly clean your data and you've got to normalize it. You might have to detrend it. You really need to work on it before just blindly shoving data into a model and hoping you're going to get something out is an extremely naive and often painful thing to do, or has painful results. Don't do it. Okay, now if you're simulating it, now I'm much more at home. So you might start off by writing a very simple model. There are very simple ways like writing sort of time marching integration solutions. If you're trying to simulate a dynamic system with an ordinary differential equation, like a 1 degree of freedom mass spring damper model, that's basically like a car wheel on the end of a spring and the shock absorber. Okay, that's great. So you can write this. And you've got this equation that goes something like m equals second derivative of x, that's the displacement, times I should have put the equation on, but anyway, you've got 3 or 4 different constants which you need to define this whole thing, but are they really constants? If you've got coil springs in your car, like in the front of wheels probably, then you can use a single variable, or a single constant to define the spring stiffness. If you've got leaf springs like you might have at the back of a car or a bucky, it's not linear anymore. Using a constant is not accurate. Okay? So what do you do about this? Well, one of the best ways of doing it is to structure your code in such a way that those things are each not constants, but functions. And you can write as many different variations of the function as you like in there. And then you can either manually or later on using an if statement, you can get it to choose one of those functions, and you can then quite easily compare how accurate different models are. And then you probably want to go to a more sophisticated model if you don't want to start off there. Okay. And like we might do a finite element analysis or something on the car. It's a lot more powerful, it's more likely to be accurate if you do it right. It requires more skill, requires a lot more computational resources and time. So you might want to use the simple model to inform where you do a breadth first search, and then you try and see where you want to do your more expensive simulation. Okay? Or alternatively, you could do a few of the expensive simulations and basically try and fit a curve over it, either using traditional models or some sort of traditional method, or even using machine learning if you want to. Okay? You generally don't want to write those unless that is your research, trying to develop a new model. Now, if you're trying to write a new finite element solver, you're obviously not going to get away from that. Okay? And of course, if you can possibly combine these things, as I said, either use your lower order model to inform where you do the simulations, use your higher order model to improve your lower order model, whatever. You try and do any of those things that you can. Don't be a one-trick pony. I do historical fencing. I try and whack people with simulations of two-handed swords. They're blunt and they're usually made out of wood or plastic. And when you're doing that or any other martial art, you don't just generally try and put the sword in the way. You try and put the sword in the way and step out of the way and distract your opponent with an attack. In the same way, you want to have multiple different layers of defense in proving that your model is correct. If you can show from your lower order model and your higher order model and experimental data and a machine learning model based on some data that you got somewhere else, if you can prove that all of those that come to it in the same, more or less the same answer, you're in a pretty good space. All right. And then just a bit of experience that I got from helping my ex-wife with she was actually dealing with data from ESCOM, I think. It was tweets, but what they did, which I think is a pretty sensible way of doing, is they used machine learning to extract those tweets which were relevant. They were looking for, in those cases, they were looking for positive or negative comments, which is a very, very hazy kind of thing. I think you'd have more chance trying to find people complaining loudly about speed bumps damaging their car. There'd probably be certain keywords, some of which you're not allowed to say in public. See, I've only got a few minutes left, or am I over time? I'm nearly done. Anyway, so you'd probably use it to reduce the data set into the things that are relevant and then extract some statistical information out of that, which you could then go and process either using traditional methods or using some sort of machine learning method. Just bear in mind, if you're doing something like this, not all data is created equal. Data from social media, I mean, most scientists are probably not going to be using that, but obviously something like that is not that reliable. Okay. So then, actually writing the code to do all this. First and most important point, break up the problem into manageable chunks. Don't just sit down and start writing code willy-nilly. Figure out what parts of the problem there are and decide which part you want to start on, and then start writing code for that. And every time you write 1 or 2 or 3 lines of code, test it. You don't write 1,000 lines of code and test at the end, you'll never find all the errors, and there'll be many. And then there's a principle called standing on the shoulders of giants. Use libraries that exist, like pandas, NumPy, Matplotlib. If you want to do a finite element analysis in Python, there are loads of libraries that will do that for you. If you want to do computational chemistry, you'll find lots of software that will do that for you. If you can find actual software that is pre-written where you don't have to write your own code at all, even better. You can usually still write little scripts to help glue that into your whole workflow. The workflow being the process the automated process you built to turn your ideas into usable data. Okay, but don't let the giant stand on you. There's a horrible library called Qt, which I still have nightmares about occasionally. When I used to work at the CHPC, I had to compile codes for people, and sometimes there'd be some little piece of software that did some simulation and it needed a date, and then they would include Qt, which is, I don't know how many 100 gigabytes. And it's really painful to compile, and there are lots of, I mean, it sounds ridiculous that compiling a library could be difficult, but if you're doing it on a supercomputer, it can. So if you can save using a 500 gigabyte library, which is not doing anything particularly fancy, by writing 3 trivial lines of code, and if you've got a really good reason to do it, just write the 3 lines of code. Stand on the shoulders of giants where you need to stand on your own feet when you can. Okay. Again, this ties in with something Ilya said yesterday as well. Use black boxes carefully, otherwise you might end up in one. You need to, even with something where you don't necessarily understand the inner workings of it, like a neural net, you need to understand the limitations of it. The person who asked about the politicians yesterday, the politicians might not understand, but it's your job as the domain specialist to understand so that you can give them good advice that they can ignore. At least then your conscience is clean. I'm being very pessimistic here, but yeah. Okay. And then write comments on your code. You will forget. I've got pieces of code I started writing 20 years ago. I can't remember, except that I wrote little notes to myself in the code. If I get ridden over by a bus, somebody can, in theory, go and look at that code and figure out what it's doing and continue my research for whatever that's worth. Okay. But at some point, you will forget what you did, and somebody else might want to use your code. So make sure you make notes on what it's. And then the last thing is use something like Git, or at least make backups, do version control. So if you make a mistake, you can go back. And if for some reason you need an earlier version of the code for some other purpose, you can actually go back and access it. And do something similar with your input data. Keep your old raw data. Don't discard it if possible, if storage and so on allow. Anyway, I think I've gone slightly over time, or 5 minutes over time already. So I'm going to shut up now. Thanks for bearing with me. And yeah.
Thank you so much, Andrew. And I hope that was useful to everyone in the meeting. So there's a question for you from Zeppo. So he says, when standing on the shoulders of giants, what happens if an existing library needs to be slightly adjusted to correctly solve a problem mathematically? Is it then advisable to tweak the underlying code, or you should build from scratch?
It depends. If it's something where you can tweak it and it's not going to make it too difficult, I mean, especially if you're using open source software, and I really hope you are if you're doing research, there's that whole idea that research is supposed to be repeatable, and using open source software for research is a powerful way of achieving that, because people don't need to pay licensing fees. If the company goes bankrupt, you still have the software. So, yeah, it depends. If you have a look at the code, if it's open source, see if you can modify it to do what you want. Make a careful note of it so you remember it, and if possible, work reversibly. In thermodynamics, there's this concept that reversible work is the most efficient, and it works in real life too. You try and do things in such a way you can revert back to how it was before. You don't damage the existing functionality, but by all means try. That's also how you grow as a programmer.
Okay, thank you. And lastly, there's a request to please upload the notes on Canvas, so the slides.
Sure, I'll send them to you guys, and then you can upload them up to the thing. That's all right?
Okay. Yes, that's fine.
Okay.
All right. Thank you so much, Andrew.
Thanks for bearing with me.
Thank you for the lessons. So guys, we are ready